not going to have to do a problem like this, but these are great problems because they combine both conservation of momentum and conservation of energy. It's a very AP-like problem. Those of you that are taking AP might be interested in this sort of problem. All right, in this situation, we have a bullet here that has a certain momentum, mv, and we have a block. So I'm going to use little b for the bullet and big B for the block. So, and this thing is hanging, the block is hanging, and it is stationary. So the total momentum of the situation right before the bullet embeds in the block, you see it just embeds in the block and stays in there. So we have a perfectly inelastic collision. Okay? So then it's going to have an instantaneous velocity in this direction that will be equal to mb/vb over m of the block plus mass of the bullet. Okay? So I'll show that in a second. And so that's going to be its instantaneous velocity. So that gives us an instantaneous kinetic energy at this h equals 0, which means it's all kinetic energy. So the idea is, how high up does this block swing? If we know how high up it swings, we know its potential energy up here. How high does it swing before it stops? So it's got no kinetic energy, okay, plus 0 kinetic energy. All right, so if we know the height, then we know that what the total energy budget is, which means that we know what the kinetic energy must have been back here. And if we know what the kinetic energy must have been back here, and that was equal to this, then we can figure out how high it goes. Hey, look, I didn't even ask you that, but I am going to solve for that. So we find the speed of the bullet and block combination immediately after the collision. That's going to be this right here. Okay, that's a conservation of momentum problem. I'll show it to you. This is definitely where we're going to arrive, but we'll just go ahead and take care of it and look at it numerically. Okay, so for part A, we've got momentum of the bullet, velocity of the bullet. That is, here, let's do this. Not momentum, that was mass. All right, momentum of the bullet plus momentum of the block is got to be equal to momentum of the bullet prime plus momentum of the block prime. Here I'm using a little b, lowercase b for bullet, uppercase B for block. All right, since we know two things. We know that the initial momentum of the block is 0 because its velocity is 0. And then since this is a perfectly inelastic collision over here, we know we're going to be able to set it up as v prime, or let's say u, because so we'll be consistent. The momentum is going to be equal to mass of the bullet plus mass of the block times their common velocity. Okay? So we don't need a subscript for that. So what do we have over here? The momentum of the bullet is equal to mass of the bullet times initial velocity of the bullet. So solving for what are we solving for? The speed of the bullet block combination after the collision. All right, so that is u right here. That's their combined velocity. So u is going to be equal to mb/vb over mb plus mass of the block. Okay, and as you can see, that's what I had right here. All right, so plugging in the data we have, 2.5 gram bullet, 425 meters per second, 215 grams. All right, so that's equal to, I have to move this over here. Mass of the bullet is, good golly, already forgot it, 2.5 grams. All right, so 2.5 grams is 2.5 times 10 to the -3 kilograms times the velocity of the bullet, which was 425 meters per second. All right, and then that is divided by the total mass, 215 grams. So, whoops, 2.5 times 10 to the -3rd times 215 grams is 0.215 kilograms. 215? Sorry. Yes, 215. All right, so we're going to go ahead and calculate that. And here, that's supposed to be added. So let's fix that. And I forgot to write kilogram. Whoops. That is kilograms. Kilograms. All right. I'm going to add that. So what we end up when we crunch all those numbers, it's going to be 4.89 meters per second. Let's make sure that's what we get. We've got, this is kilograms, kilograms and kilograms on the bottom since they're added, or kilograms and kilograms. That does leave us with meters per second, which is what we're looking for a velocity. So the correct answer is 4.89 meters per second. Now, I did not assign this, but what makes this a cool problem is it's a combination conservation of momentum problem, which is what we have for A, and conservation of energy problem, which is what we have for B. So let's come down, and even though I didn't assign it, it's kind of cool to know how to do this problem, and we will do a conservation of energy problem. All right, so what is conservation of energy? We know that the kinetic energy at the bottom plus the potential energy at the bottom has got to be equal to the kinetic energy at the top plus potential energy at the top. And you see I'm using zero subscripts for what's going on at the bottom. Well, the potential energy at the bottom, if we take that level to be 0, all right, we're going to take this to be here, to be h equals 0, right here. And then we're looking for what the height is when it gets up to the top, okay? And when it gets to the top, it's instantaneously at rest, so its kinetic energy is equal to 0. So we have 1/2 mv squared is equal to mgh. Now, it's worth pointing out that m here, this mass, is equal to the total mass of the block, or the bullet plus the block, but as it turns out, it doesn't even matter, does it? Because it cancels out on each side, because it's stuck together right here, and it stays stuck together up here. So, all things told, doesn't matter. So here we get 1/2 v squared is equal to gh, so solving for h is equal to v squared, that's our velocity at the bottom, over 2g. And like some of you recognized before, that looks exactly the same as when we solved for maximum height for a projectile fired straight up in the air. All right, so we go back here, and we will use a calculated value, even though that's sort of taboo. 4.89 meters per second, and we're going to square that. And 2g is going to be 2 times 9.8 meters per second squared. So we get meters squared per second squared divided by meters per second squared gives us meters. Okay, that's what we want because we're looking for a height. All right, so now we'll go ahead and crunch those numbers. And we get that h is equal to 1.2175, so we'll call it 1.22 meters. That's the height that the block swings up to, right, center of mass to center of mass, as a result of its initial velocity here, swings up to where its kinetic energy is 0 and its potential energy has to be equal there, 1.22 meters.